Nothing. I don't even know what you're talking about. All right. So once again, a displacement reaction. Ions oxidize in elements. An element, the ions then are reduced. These are actually usually pretty simple. They're usually very easy to balance as well. So it shouldn't be too bad. So in this example, most likely what we had here, we had copper metal, and we added AgNO3. And then we end up with Ag solid plus CuNO3 2, most likely. You don't need to write that down. But what's happening is this right here was in solution, the Ag plus, correct? All right, and it reacts and becomes a solid. That's why this copper became silverish grayish looking. So it goes from +1 to 0 or neutral. So +1 to 0. So it did something. And then copper, it goes from a 0 to a +2. You with me so far? Why is this a 0? Because it's just the element. Why is this a 2? All right, because it's with 2NO3, that means it is a +2. Copper is almost always a +2. When in doubt, guess that. It can be a 1, but it's almost always a +2. All right, if you go from 0 to +2, you lost electrons, right? Or you were oxidized. You okay with this? So this must have gained electrons or it was reduced. Uh-oh. It's an early break for my slate. All right, so it was reduced. So the displacement reaction, ions oxidize an element. All right, so the ion, the Ag plus, caused the copper to be oxidized. Causing that oxidation means then it is reduced. All right. So this is just going to say pretty much what I just said. In this reaction, silver ions oxidize copper metal. All right, now, in order to know if it's a displacement reaction, which last year we called a single replacement reaction, you have to have a lone element reacting with a compound. We knew this was in a compound because it is written as a plus. It had to be delivered somehow besides just solid silver, so it had to come in solution like a nitrate, a sulfate. Well, not sulfate, but nitrate or acetate for silver. All right so far? Okay. This reaction, as written, would not work because there is no electromotive force to cause it to go the other direction. Hold on, I didn't mean to write that. Okay, so silver, I said silver, copper cannot cause silver to be oxidized. Only silver can cause copper to be oxidized. All right. The way to know whether something works or not is to understand what we call the activity series. All right. So the activity series is generally a list of elements in their oxidation reduction, or reaction, I should say, right here. All right. Sometimes it'll even give numbers right here, which we'll learn in chapter 17, what those, or 19, what those numbers are. But right now, all we care about is where things are. So you can see, well, you can't see that very well, but that's the oxidation easiness. The higher you go, the easier it is to oxidize. So it says in order for a reaction to proceed as written, the lone element must be higher on the activity series than the element written as an ion. So what we do, and 4 of you already did your homework. That means 36 of you have not. It's a good average, right? Because set 3 was due today on the calendar. Well, they both were. Step 3 did not take very long, right, Timber? Right, Iverson? It really was very fast. All right, so what we do is we look at the reactants side only. For this right here, like these are important, but not for this question. So to determine whether it actually happens or not, we simply look at the reactants and the lone element. So which one of these is the loner? Copper, because remember, if it was a plus, it was with something else. How come the something else isn't written here? It's a spectator ion. But in the problem they give you, it would say word-wise, copper plus silver nitrate. Then that's easy, right? Copper is the loner. Silver nitrate is the thing that's an ion. All right? So the lone element must be higher on the activity series than the element written as an ion. All right. All right, just had to double check that I wrote that right. I wrote that this morning. All right, so if you see copper here, and this is ease of oxidation, it's hard to see probably, but silver is right below it, which means that it is harder to oxidize silver than copper, or the reverse, it is easier to oxidize copper, or silver can oxidize copper. If it was written the other direction, it would not work. Okay? So I would write this sentence down. This is super important. Hello, Randy. So go ahead and give these a shot. Okay, let's go ahead and work through these. Hopefully they'll make pretty decent sense. So, did I ask you to write out the whole thing? No. So what I did, I put Ni, if it's the metal, it means it's the solid, right? And I have copper 2 nitrate, so I don't care about anything but the Cu plus 2. So now what I'm looking for is nickel, which is right here. And I'm looking for copper, which is right here. Is the lone element higher on this chart than the ion? Yes. So will this happen as written? Yes, it will. Did you guys have that wrong? Girls are evil, Jack. That's what you've learned in chemistry today. Just kidding. Number 2, hydrochloric acid is added to silver metal. So silver metal is the solid, right? Hydrochloric acid, it might seem like it's hiding, but this is H+. You okay with that? So now we're looking at silver. It is here. Hydrogen is here. So is the lone element higher? No. So will this happen? No. You okay with that? All right. Same process. Chromium metal, so Cr, that's my solid. And cobalt 2, so Cl plus 2. So I find Cr, it's right here, right? And cobalt. Is my lone element higher? Whoa, that was bad arrow drawing. Yes, it is. So will this happen? Yes, it happens as written. Calcium is added to a solution of sulfuric acid. This is heck yes, it'll work, but this is why. So calcium would be my solid, right? Sulfuric acid is supplying my H+. Calcium is way up here. Hydrogen is way down here. My lone element is way higher than my ion, right? So this happens, and it happens vigorously. If you put calcium in that acid, it will bubble a lot, produce a lot of heat. All right. Now, The question Logan asked me a minute ago was, do I have to memorize this chart? The answer is no. You do not have to have it memorized, but there are some things that you should know about it. Oh yeah. I don't have detergent, I just have that stuff. All right. So notice right here, this is the top, and these are family 1 and family 2. Okay? It doesn't necessarily matter what order they are in because they'll ask you pretty far away. So family 1 is the most reactive. We should know that. And down here, my ring is made out of gold for a reason. How come? Because it doesn't react with anything, really. I want this ring to last forever, right? Okay, so you should know family 1 and 2. They're at the top. You should know your precious metals are at the bottom. Then, you should know hydrogen is just barely above. So, this means that acids will react with everything except for copper, silver, mercury, platinum, and gold. Okay? So, know that this is just barely above your precious metals, and then iron is in between them. If you know those things, you should be just fine. Most of the time, if they ask you this, they'll give you something on the test. All right, that's the activity series. That is how we know if a displacement reaction as written will happen. Did I unmute this thing? Test? Yep, I did. All right. Who's okay with that? Okay. So let's take a time out before I get into this next part and talk about your exam. All right? Because that's what you really care about in life, correct? The Chapter 4 test is very hard. Smiley face? It's super hard. But you'll be okay. I'm pretty sure. All right, so if you're not, you're host. You have to be able to write net ionic reactions. This is like the start of everything we're going to do. But these will be really, really important. All right, you have to be able to write net ionic reactions for acids and bases, including gas-forming reactions. All right, you have to be able to do that. Not number 3, but you also have to be able to write, I'm going to put simple redox reactions. So not like the super complicated ones. We will certainly get to those, but that's in a chapter a long way away. You're welcome. Just basically you have to be able to identify what's losing electrons, what's gaining electrons. You all right with that? All right. Then you have to be able to apply the activity series and write out imbalance reactions that do happen. If you're lucky, well, there are 1 or 2 that don't happen, so all you have to do is put no reaction. There's 1 or 2 homework problems exactly like that are very, very similar to the ones on the test. Okay, then pretty much the rest of this test is math. That's my attempt to write the word stoichiometry, which probably better to you in your mind is a limiting reactant problem. But this time we do a limiting reactant with solutions. I hope that most of you were able to watch those videos and that they were at least somewhat quality and you were able to learn. I'm going to collect your papers at the end of the hour. But that's kind of your introduction to this grand idea of solution stoichiometry. The good news is we've already done it. The only thing we're doing is changing to concentration since these are happening in solution. So to introduce that, we've got to start off with this term molarity. Molarity is a new word unless you watched the videos or had regular chemistry. All right, molarity is one way to measure the concentration of a solution. In this class, molarity is the most important way that we measure the concentration of a solution. Now, molarity has its own short abbreviation, and that is just a capital M. Molarity, or capital M, is equal to the moles of solute over volume of solution in liters. Now, one of the big dangers is when you just write a capital M is you don't realize that you have a proportion. So just make sure that you're good and that you know capital M means two things. It's moles over the volume of a solution in liters. Okay? So all these problems, we're going to have to end up with molarity. So every single thing that we do, we're going to have to eventually get them converted to moles. And we're going to have to know the volume. The volume's the easy part. All you have to do is add, typically. Sometimes you have to move the decimal, but it usually is not hard. So we just have to figure out the amount of moles. Who's with me so far? Good. Thank you. All right. And we'll make this more complicated in a minute. But generally, it will tell you a volume and molarity of a solution. So for instance, it'll say you have 250 milliliters of 0.4 molar AgNO3. This is most typically the way that the problem would present it. So it gives you just your volume, it gives you your molarity, but we need to know the amount of moles of both parts of this. Now this one will be easy because it's just a one-to-one. But what we would do to find moles, we just use our brains. If this is 0.4 moles per liter, how do we get rid of liter? You just multiply it, right? Liters disappear. I'm left with moles. So I would just take this, multiply that, and get 0.1, right? So if I had this solution, I would have 0.1 moles of Ag and 0.1 moles of NO3 minus. We all right with that idea? So in order, you don't have to write a picket fence, but in order to find your moles when you're given those things, you just multiply the two numbers by each other. You have to make sure you're in liters though. So hopefully you know, but if you don't, you move the decimal 3 places to the left to find liters. Okay? Let's do 1 and then we'll move on a little bit. So how about you have 800 milliliters of 0.3 molar, I don't even care. And no, let's go MgCl2. So what I want to know are the moles of Mg plus 2 and the moles Cl minus.
What first number?
800 milliliters.
Okay.
Didn't I say 800?
Yes. That's all that's what pay attention to.
It's okay. I think my writing looks really good, personally. I always have been. Yeah. All right, so if you follow what I just said, you now convert this to liters. So it's 0.8 liters. And then we can just multiply both numbers, right? So 0.3, does that equal 0.24? Okay, now hopefully you're all okay with this because you watched the video, so I'll just assume you all did. That is the concentration of Mg. But it is not the concentration of Cl2. How come? Okay, because for every one of these that breaks apart, we produce 1 Mg, but we produce 2 Cl minus. So this would be 0.24, and this would be 0.48. All right with that? Brackets, that's our concentration. That's a lot easier than writing the word concentration. So we would have 0.24. Oh, whoa. I'm sorry, that wasn't concentration. That was just moles. I apologize. I'm an idiot. Oh, well. We were not finding molarity here. We will later, but sorry, that was just moles. We good with that? All right. Now, I'm going to save this one and open up the other one. All right. I think that my videos tried to follow this same process. If there's wrinkles or not, I don't know. I made the videos a few years ago, and I am not a super consistent human being. All right. But to solve what we call solution stoichiometry problems, we do the following steps. You'll be given a problem most likely in words. The first thing you have to do is write and balance. I guess right off the bat, I didn't write that word. That's the ugliest R ever. Write and balance the reaction. So forever ago, we talked about this. Hopefully it's something you've developed a good skill at. Number 2 is determine the precipitate by using solubility rules. You do not have to have those memorized. I have this little paper that I hand out when you take the test that will help you with that. I might as well hand this to you now, but don't take it because I don't want to. Oh, look at that. Okay, well, he must have retired and killed his site then, because it was Mr. What's-His-Face from Springville. I don't know why I'm here. Everyone gets one. So I will change that. Thank you. Good morning. All right, so we would determine which thing will be a precipitate by using our solubility rules. The third step we would do would be to find the limiting reactant by looking at moles given or by using both given moles to solve for grams of precipitate. Mark, is this following the same basic outline? Okay. Then we find the grams of precipitate, which you already might have done. Number 3, you can do in 2 different ways. If you do it by finding grams, then you've already done number 4. Number 5, find concentration of each ion at the end by doing these things, which they don't look too difficult. Letter C is pretty hard. So A, the concentration in the limiting reactant and precipitate equals 0 grams. The video tried to explain that. It's the one that runs out, and it's the one that's no longer in solution. So its concentration will be 0. Spectator ions equal the initial moles over the new total volume. Those, I like those a lot. They're very simple. All you have to do is find the moles you start with, add the 2 volumes that were mixed together, and just divide. Letter C, this is the hardest one. The concentration of the ion in precipitate and excess reactant is equal to initial moles minus used moles over total volume. So we have a problem we'll work through together right after this. All right, I'm going to move on pretty quick, so write faster or take a picture of it. All right, so here we go. So we have silver nitrate plus sodium chloride. And then let's finish it. And this will be super easy as far as chemistry is concerned because everything's a 1, right? All right. That makes silver and who over here? Plus Na and who? All right. Using our solubility rules, I don't even know if this will, it won't tell you what is, but it'll definitely tell you what isn't. So which one is definitely not the precipitate? This one, right? So this must be my solid. Okay? So now we didn't balance it yet, but we don't really need to because it's just ones. Good? All right, what's our next step to do then? Determine what? Limiting reactant. Now, there are 2 ways to do this. And there always has been, by the way. I only taught you one. but whatever, we can still be friends. So the first thing I would do, I would convert both of these to the number of moles. So how many moles do I have of silver nitrate? That one wasn't difficult, right? You just multiply the two numbers. I have 0.3 moles of silver nitrate. How many moles do I have of NaCl? That's 0.2. Can't be 0.2. 0.8, right? Down here, it's not just 0.8. Four times 2 is 8, but there's a decimal, right?
That looks like a 2.
Oh. Okay, because I was super lost.
That looks like an L2.
Like, when did people stop being able to multiply 2 times 4? Is that any better?
Yeah.
All right, my fault. Usually it is. All right, so I have 0.8 moles of this. Okay, now, right off the bat, we can actually determine the limiting reactant right now. Like, we could go ahead and convert to grams. You can do that too, but we can also look right here. The limiting reactant, if this is a 1 and that's a 1, then the limiting reactant is the one with what? Less. That's pretty simple, isn't it? So our limiting reactant will be AgNO3. Did that make sense to everybody? All right. Now, most of the time in these, I would do it that way because I'm not giving you grams that you have to convert to moles, because, and that's not that big a deal, but you can't do that in your head generally. These ones you can kind of figure, and then all you have to do, let's pretend, and it's not, but we're pretending right now. Let's say this was a 2. If it's this way, then you just have to say, all right, is this number 2 times that number? That's how you would determine the limiting reactant now. You kind of with me? All right. Now, it's just ones. So now we know this is our limiting reactant. Okay. That was step number 2. What's step number 3? Yes?
So would we just divide the moles by the coefficient, and whichever one is less of the
All right. Step 3. Oh, we're on 4. What did I do then? Oh, right and balance. I forgot. Okay. So we're on 4, so we're finding the grams of precipitate. All right. So now, get rid of this. Okay. Okay. Here we go. So I'm going to set me up a nice, cute picket fence here. And what am I going to be solving for? Grams of who? All right. And what am I going to start with? My 0.3 moles AgNO3. How come I'm starting with that? It's my limiting reactant. All right, so what has to go on the bottom then? Like from here, we're set, aren't we? So we have 1 mole AgNO3. And do not put the molar mass of AgNO3 on top. Do we need the molar mass of AgNO3 in this problem at all? No, because we're already in moles, right? So what does go up here? Good. 1 mole AgCl. What goes on the bottom of the next one? One mole AgCl. And what goes up on the top? Grams. So 108 plus 35.5, 143.5, right? Somebody type that up for me. Let's say 48.2. Oh, I am terrible, but it's a Monday. 43 point what? Good enough. Okay, this isn't terrible, I hope. Even Caleb hasn't complained about it yet. Okay. All right. So what's the next step tell you to do? Okay, Spectator, no, Spectators wasn't first, right? So concentration of ion in precipitate and limiting reactant. We know that's 0, so all we have to do now is figure out what ion is in both of these things. So we have this and we have this. What ion do they have in common? Silver, right? So the concentration of silver is 0. What, Newman? Well, you put your head sideways. That means something. What don't you like about it? You don't like nothing. That means you like everything, right? Did it make sense? Because if it doesn't make sense to you, everyone's hosed. Okay, remember, precipitate means it's become solid. So is this even in solution? No. Limiting reactant is the one that is completely used up. So to combine those, it says that this one is completely removed from solution. That's silver. Okay, in the notes, we had next the concentration of spectator ions, right? The concentration of spectator ions. Bueno? All right, and we said those are equal to their moles over the new volume or total volume. So one of them is NO3, right? I'll scroll up. All right, so NO3 minus, we have to find its initial moles, which was equal to the silver, right? So it is 0.3. Oh, this does this a lot. And then we have to find the new total volume, which is 3 or 0.3 plus 0.4, or our new total volume is then 0.7 liters. What's that? So that's equal to my NO3. And then we'll do the same thing with the other one. Was that Na, right? And it had 0.4, didn't it? No, 0.8 to start. This answer. All right, and the denominator is still the same, 0.7 liters. So now we have 1 point something, 1.8. What? 1.4. All right. So far, who's okay with this? Okay. I'll take a wobbly hand right now. That's That's not that bad. All right. So now the good news is if you got all this right, you're like at 90%. So the next part is the trickiest part, but you can still get an A and still bomb this. But let's try to not. All right, so what thing is in the precipitate and in the excess? So we're talking chlorine now, right? Or chloride. Oh my gosh, whatever. Cl minus. Okay, is in precipitate and excess. Okay, so we need to know the initial moles, which we already calculated early. That was what? 0.8 moles. All right, then we need to know the used moles. Okay, and it's not as bad as you think. The used moles will be determined by the limiting reactant, right? Okay, so my limiting reactant was 0.3 moles of Ag. You could put AgNO3, it won't matter right now, either one. Ag plus. I need to get rid of moles Ag plus, so it's 1 mole Ag plus. And then I want to end up with moles Cl minus, right? So this one's easy because it would be 1 mole Cl minus. So the amount of moles that can be used in this reaction will be equal to 0.3 moles used. All right? So I just put that up there. Now, I need to subtract these, right? So the excess moles will be equal to 0.5, right? And then to find concentration, I always have to divide by what? By my new total volume, which was 0.7 liters. And I'll end up with some number. 0.76, I don't know. I'll tell you in a second. What was this answer? 7.1. Whoops, I keep doing it that way. It doesn't matter. All right, so Kylie asked where I got the 0.7, and I know you're not the only one with that. We are going to use 0.7 multiple times because it's the total volume when you pour both things together. It's the denominator 3 different times. Go ahead. Because they will ask you that in the problem. It's just an answer. Yeah, you don't need it for something later. It's just an answer. No, you can. You can certainly, you can use this to start all your picket fences, but then you'd have to use its molar mass and the other molar masses, and you made something 5 pickets long instead of 3. All right, so now the answers to the test. There's lots of them here. Let's put them in big black. So how this would be scored, this would be 1. The balanced chemical reaction, whatever. That was supposed to be a box. All right. Other things that would be scored on this is your ability to determine the limiting reactant. Wow, this was black, but now it's blue. Whatever. All right. Well, that one I was just dumb. Here we go. It's black and blue and red all over. All right. So you would get points for that. You would also, on the AP test, for sure, you would get credit for calculating the amount of moles of each present at the start. All right? you would be asked for and given credit for finding the mass of the precipitate. Then you would get points for the concentration of all of your ions. I don't know if it's the hardest, especially for you, because you've had chemistry before, but it's typically the hardest part of the test. No, this is it. This is the end. Yes. That's which one? Right here? That is the molarity. That's why I have a bracket here. If you put a bracket, you don't have to put M. If you don't put M, put brackets. If you do put M, you don't have to put brackets. It's just, that'd be redundant, which is fine. Okay. I think Colin thinks this really isn't that hard. Is that right? Okay. It gets trickier when you have subscripts. It gets significantly harder. So here's one that we'll work on tomorrow if you want to try it and get a head start. I guess I don't have enough information on this screen. Let's see if there's one I do have. There's one. All right. If you have that assignment from the weekend, no matter what condition it's in, turn it in so I can at least see that you did something. Put it on one of the tables on the way out of the door. The what? A couple people still had questions. Remind me to go over it tomorrow to start, and then we'll turn it in.